My name is Horvath. I'm PhD student at KAUST, and today I'm going to present you our work titled FJORD, Fair and Accurate Federated Learning under Heterogeneous Targets with Ordered Dropout. This is joint work with Steve, Mario, Stelios, Elias, and Nick. Let me start with the problem we are tackling. One of the key challenges of deploying federated learning in the wild is the vast heterogeneity of devices ranging from load and IoT to flagship mobile devices. Despite this fact, the widely accepted norm in federated learning is that the local models must share the same architecture as the global model. Under these assumptions, developers typically opt to either drop low-tier devices from training, hence introducing training bias to answer data, or limit the global model size to accommodate the slowest clients, leading to degraded accuracy due to the restricted model capacity. In our work, we realized that not every client has to run the same global model, and we have introduced a novel adaptive training framework that enables heterogeneous devices to participate in FL by dynamically adapting model size and thus computation, memory, and data exercises based on the client's local and network constraints such as memory, computational capabilities, load battery level, or limited bandwidth. As such, FJORD enables all devices to participate in the FL process independently of their capabilities by training a submodel of the original DNN while still contributing knowledge to the global model. To enable this dynamic adaptation of model size, we introduce Ordered Dropout. Ordered Dropout is a mechanism for runtime ordered pruning, which enables us to extract and train submodels in a nested manner. Our proposed OD method is parameterized with respect to the set of relative submodels with values and the sampling method over this width. To get better intuition, we compare our ordered dropout with random dropout. For random dropout, for each hidden neuron, we drop it independently with given static probability T, which acts as a regularization technique during training, and for deploy model, no dropout is applied. Our ordered OD acts in a bit different way. Apart from regularization, it is rather network pruning technique. During training, in each iteration, we sample a width that lies in interval 0, 1 from given distribution, and we keep the most left neurons that lies in the sample width. For example, here in the first hidden layer, we might have sampled width 0.6, and therefore we keep these 3 neurons out of 5. Note here that the leftmost neurons are used more during a training, creating a natural ordering to the importance of these neurons. For the model deployment, we can then dynamically select any width from possible submodels to accommodate current local constraint of the given device. With respect to OD's theoretical properties, we showed that if there is a linear dependence between features and responses, OD exactly recovers singular value decomposition. Let us look at the following optimization problem. That can be seen as a problem of fitting 2-layer neural network with no activation. In our paper, we showed that applying ordered dropout here along every width with non-zero probability regularizes the set of optimal solution. And for each optimal solution, it has to hold that up to scaling, it is equal to SVD decomposition of S. Therefore, it leads to best V-rank approximation of target mapping S along every width 3. Building upon the shoulders of Ordered Dropout, we introduced FJORD, a framework for federated training over heterogeneous clients. As a starting point, the global model architecture is initialized with weight, either randomly or by a pre-trained network. The Ordered Dropout array space is selected with discrete candidate values where each relative width corresponds to a subnetwork of the global model with varying flops and parameters. Next, devices to participate in training are clustered into given number of tiers, here 3, and each cluster C is assigned with its PC max that represent the maximum capacity of the model that devices in this cluster can handle without violating a latency or memory constraint. At the beginning of each communication round, the set of participating devices is determined, which either consists of all available clients or contains only a random subset of available devices based on the server capacity. Next, the server broadcasts the current model to the set of clients, and each client receives the model of maximal width, doesn't violate its constraint. On the client side, each client runs local iterations, and at each local iteration, the ordered dropout is applied to local model. At the end of the local iterations, Each device sends its update back to the server. Finally, the server aggregates these communicated changes and updates the global model to be distributed in the next global federated round to a different subset of devices. Heterogeneity of devices leads to heterogeneity in the model updates, as it can be seen from the coloring used here. For the inference, the deploy model is adjusted based on the device constraint. Furthermore, OD comes with built-in extra benefit of producing models that can be dynamically scaled during inference based on the current constraints of the device, for instance, based on the battery level or current load. For the evaluation, we start with the preliminary results. We present some results to showcase performance of OD in the decentralized non-federated learning training settings, which means that the server has access to all training data. On the top of OD, we employ knowledge distillation as nested structure of ordered dropout allows to use a model with a full width as a teacher for sampled subnetwork. We consider two classification tasks. Concretely, Amnis dataset with two hidden layers convolution network and Shakespeare dataset with LSTM network. For the baseline, we chose end-to-end trained submodels trained in isolation for the given width of the model denoted by SM, and end-to-end trained full model with random dropout instead of ordered dropout denoted SM1 with random dropout. For the ordered dropout distribution, we consider uniform 5 and 10, which are uniform distributions over 5th and 10th respectively. Uniform 10 is only used in the last experiment. For the first experiment, we compare ordered dropout with the best single models. Our results show the performance of ordered dropout along every width is very close to the performance of the baseline models. While we know that submodel baselines are trained from scratch, explicitly optimized to that given width, while our ordered dropout model was trained using a single training loop and offers the ability to switch between different widths without the need to retrain or fine-tune. For the second experiment, we add a different baseline where we take the end-to-end trained full model and create random submodels from it using random dropout. One can note that such strategy is not comparable to ordered dropout and leads significantly worse model performance. Lastly, we show another important characteristic of ordered dropout, which is its ability to scale to a large number of devices clusters, or equivalently, perform well with high granularity of width values. We illustrate this by comparing uniform 5 and 10 distributions. Next, we introduce our setup for the federated learning experiments. Similarly to centralized setup, we employ knowledge distillation with the difference that a teacher network is a model with the largest local width. We consider the same task with non-IID client distribution. We consider two baselines that are able to accommodate all clients in the training process: federated dropout and extended federated dropout. Federated dropout adapts a random dropout at neuron level for minimizing the model's footprint. However, federated dropout does not support adaptability to heterogeneous client capabilities out of the box, as it inherits a single dropout rate across devices. For this reason, we propose an extension to federated dropout, allowing to adapt the dropout rate to device capabilities defined by the respective cluster membership. In the paper, we show that this extended federated dropout is tough baseline, and therefore we only include EFD here. With respect to client clusters, we consider 5 clusters with maximal width 1.8 down to 0.2, with 20% of devices in each cluster. For the ordered dropout distribution, we consider the same ones as for the centralized setting. If not mentioned otherwise, uniform 5 distribution is used in our experiment. In the first experiment, we compare our method to the best single model using extended federated dropout. We show that FJORD significantly outperformed this baseline. Note here that for the EFD, the performance doesn't necessarily increase with the wider, more complex models, as single larger models can't be properly trained on multi devices due to the presence of large dropout values. This is not the case for our FJORD due to its built-in nested structure. Subsequently, similarly to non-federated baseline, we showcase that FJORD's scalability to an increased granularity of model width is not affected by more challenging federated learning setup. In conclusion, we have introduced FJORD, a federated learning method for heterogeneous device training. To this direction, FJORD builds on top of our ordered dropout technique to extract submodels of smaller footprints from a main model in a way where training the part of the model also participates in training the whole model. Thank you for your attention.